All right, everyone. Hello. Today we're going to talk about the reactions of acids. Our goals for today: to write balanced equations for the reactions of acids. We want to predict the acid and base that are needed to make different salts, and we want to calculate concentration of an acid or a base using data from a titration experiment. So, reactions of acids. There are 4 common types of reactions that acids go through, and for each of these, we would like to, first of all, identify the general form of the reaction, right? So we already did that with acids and bases. Acid plus base yields salt plus water. That's the general form. We want to, if we're given the reactants, be able to predict the products, and then, of course, balance the equation. So the first reaction we'll talk about is the reaction of an acid plus a metal. So the general form for this reaction is acid plus metal yields salt plus hydrogen gas. So the metal has to be above hydrogen on the activity series. So here's our activity series. Hydrogen is right there. And so any metal that's listed above hydrogen will react with an acid, but if you are below hydrogen, you will not. So this shows a picture of magnesium in hydrochloric acid, and you can see there's little bubbles of hydrogen gas forming there, so that is a reaction that goes. But something like copper in hydrochloric acid, we don't see any reaction at all, so it has to be an active metal. And when this reaction happens, we can observe effervescence or bubbling. And we'll see that on the next slide in a little GIF. There you go. You can see a little piece of magnesium being dropped into some hydrochloric acid, and you get some pretty vigorous bubbling. So you can describe that as effervescence. So quite obviously reacting there. Now, we said an acid plus a metal yields a salt plus hydrogen gas. We hear that term salt a lot. So what is a salt? A salt is a compound formed when the H+ ions in an acid is replaced by a metal cation or ammonium. Right? So if we have the acid, for example, hydrochloric acid, HCl, if we replace the H+ in there with a metal cation, then we could get a salt like table salt, sodium chloride, or magnesium chloride. Right? So those are chloride salts. An acid like H2SO4 would make sulfate salts. So the hydrogen ions are replaced by a metal cation or ammonium. So that first one, ammonium sulfate, is a salt, and so is calcium sulfate. Right? So that's what a salt is generically in chemistry. When we say salt, we're talking about a group of compounds, not one specific compound, like when we're cooking. Okay, let us predict some products here. Okay, so we're going to mix nitric acid and magnesium. Those two react. What are the products going to be? So remember, we're going to have the magnesium replace the hydrogen, and so we have to think about the ions that are present. So the nitric acid is made up, there's one hydrogen there, so that's an H+, and since there's only one, that tells us that the nitrate ion must have a charge of -1. Now, magnesium, when it forms an ion, it's in group 2 on the periodic table, so it has 2 valence electrons. It loses those 2 valence electrons, and it makes an ion with a 2+ charge. So when we put these two together, the magnesium and the nitrate, we're going to need 2 nitrates to balance the 2 positive charges. So the formula there is Mg, and then in parentheses, NO3, 2. And the other thing we get, of course, is hydrogen gas. Hydrogen's a Hofbrinkel, so it's H2. And then we can now see if the equation needs to be balanced. So I have 2 hydrogens on the right and only 1 on the left, so I'll put a coefficient of 2 in front of HNO3. That gives me 2 nitrates, which is what I have in my magnesium nitrate, and my magnesiums are balanced, so that is a balanced equation. All right, let's try another one. This time we'll react H2SO4 and aluminum. So aluminum, again, is above hydrogen on the activity series, so this will go. Now we have to remember what charge aluminum is going to make as an ion, and so it's actually in group 13, right? So you go group 1, group 2, and then you have the transition metals and aluminum in group 13, so it has 3 valence electrons, and so it's going to make an ion with a +3 charge. Now, what charge does the sulfate ion have? Well, I see 2 hydrogens here, so that tells me that sulfate must have a -2 charge. And so in this case, if I think about crisscrossing, I am going to need 2 aluminums and 3 sulfates. So that is Al2 and then SO4 3 plus my hydrogen gas. And so there are my products. Now let's balance the equation. Let's see, 2 aluminums on the right, so I will put 2 in front of aluminum on the left. I have 3 sulfates on the right, so I will put 3 in front of H2SO4, and that gives me 6 hydrogens, so I need a 3 in front of H2, and my equation is balanced. And if you're having a hard time remembering the charges of the ions, just pull out your ion sheets and you can look those up. The second type of reaction acids go through is that they react with metal carbonates. So our general form here is an acid plus a carbonate yields a salt plus water plus CO2. So again, we see that salt in our product. That'll become familiar. We also see CO2, which is a gas. So when this reaction happens, we can tell it's happening because we will observe bubbles. So let's do an example. So here we have hydrochloric acid HCl plus calcium carbonate, CaCO3. So calcium carbonate you find in eggshells and seashells and limestone and marble. It's the major component of all those things. It will react with HCl, and what will the products be? Well, we need a salt, so that's going to form from the anion in the acid and the cation in my metal carbonate. So I'm putting together a chloride ion and a calcium ion. Calcium has a +2 charge, right? If I didn't know that, I could check my ion sheet. And so the formula for my salt is CaCl2, and then my other products are water, H2O, plus carbon dioxide, CO2. And then I can check and see if my equation is balanced. So in terms of calciums, 1 on each side. Chlorides, I have 2 on the right, so I need 2 in front of HCl on the left. That gives me 2 hydrogens, which I have 2 hydrogens in water on the right. And then I didn't check my carbons. 1 carbon, good on both sides. And then my oxygens, there are 3 on the left, and I have 1 in water and 2 in carbon dioxide, 3. So that equation is balanced. Right, here is a little GIF showing us a reaction between hydrochloric acid and calcium carbonate. And we see that vigorous effervescence, that's the carbon dioxide gas. Okay. So we'll also mention that the carbonate can be a hydrogen carbonate as well as just a straight carbonate. So an example of that would be nitric acid reacting with sodium hydrogen carbonate. The products are exactly the same. We still get a salt, water, and carbon dioxide. So let's write our products here. So our salt is going to be forming from the anion in our acid and the cation in our hydrogen carbonate. So both of those have a +1 - 1 charge. So our formula for our salt is NaNO3, sodium nitrate, and then we get water, H2O, plus CO2. And if you check through there, we don't need any coefficients. That equation is balanced. So hydrogen carbonates react in the same way as carbonates. All right, third reaction, acid plus ammonia. So an acid plus ammonia makes just an ammonium salt. So essentially what happens is the proton in the acid gets transferred over to the ammonia, and it makes an ammonium ion. And so super straightforward, just kind of mushing them together. So HCl plus NH3, our ammonium salt, the hydrogen is going to join with the ammonia to make an NH4 plus, and then that's going to combine with our anion, our Cl minus, And so our product here is just NH4Cl ammonium chloride. Right? So chloride has a -1 charge, so I just need 1 ammonium. If I had an acid anion that had a different charge, like the phosphide ion here, my phosphide ion is PO3 then when the ammonium forms, I'm going to need 3 of those. So NH4 plus, I will need 3. So my product is going to be NH4 in parentheses 3 PO3, ammonium phosphite. And then I will need 3 in front of the NH4 there. Okay, last reaction, and this is the one we already talked about, is an acid plus a base. So we know this one, we're familiar with it. An acid plus a base yields a salt plus water. So in this case, the base is one of 2 things. It's either a metal hydroxide or a metal oxide, and we'll do an example with both of those. This is also known as a neutralization reaction because the acid and the base kind of cancel each other out. And a little factoid about acid-base neutralizations is that they are always exothermic. They give off a little bit of energy, so the solution would warm up when you do this. Now we're going to see this in the context of an acid-base titration in our lab next time, so we'll start talking about that in a few minutes. So when we do an acid-base titration, we're doing a neutralization reaction. But before we get to that, let's just predict a couple of products. So first, let's react ethanoic acid with sodium hydroxide. Now, ethanoic acid is an organic acid, and so it's kind of a little bit different. The H on the end, that's our hydrogen ion, and then this is our ethanoate ion, so CH3COO minus. So when you see an acid like ethanoic acid, it's actually the hydrogen on the end that gets donated. And then we're putting, so our anion, ethanoate, we're putting that together with our sodium cation. And so our products are going to be sodium ethanoates. And okay, we're taking our H and our OH and putting those together to make water. And so 1 sodium, 1 sodium, 1 ethanoate, 1 ethanoate, 2 hydrogens and 1 oxygen. This is balanced. Okay, here's an example where we're reacting a metal oxide instead of a metal hydroxide. Okay, and they react and form exactly the same product. So we'll use calcium oxide as our oxide, reacting it with phosphoric acid H3PO4. So our salt is going to be made from the anion PO4 3-, and then calcium is our cation. It has a charge of 2+. And so I'm going to need actually 3 calciums, Ca3, and then PO4, 2. And the hydrogens and the oxygen are going to come together and make our water. And so to balance this then, let's see, I need 3 in front of CaO to make 3 calciums. I need 2 phosphates, so I'll put 2 in front of H3PO4. That gives me 2 times 3 is 6 hydrogens, so I need 3 in front of water, and then I have 3 oxygens, so that one's balanced too. Okay, question. What acid and base could combine to make the salt calcium nitrate? So remember, salt, the H plus is replaced by a metal cation, so there's calcium nitrate. So the calcium ion has to come from the base, and we said bases can be either hydroxides or oxides, so it could be either calcium hydroxide or calcium oxide. And then the nitrate ion has to come from the acid, that's our anion, and so the acid there is HNO3 nitric acid. Okay, so those are our 4 types of reactions. Acids react with metals, they react with metal carbonates, they react with ammonium, and they react with bases. And now we want to focus for the end here on that last little reaction of acids and bases and see how that applies to something called titration. So titration is a method for determining the concentration of a solution by reacting it with another solution with a known concentration. So essentially you have a solution that you don't know the concentration of, but you would like to. And so you can use a solution that you do know the concentration of to find the concentration of the unknown solution. So you mix the solutions together until you reach an endpoint that's shown in our experiment with an indicator to show the reaction is complete. We'll track the volumes of both of those solutions really carefully, and then we'll use that information to calculate the concentration of the unknown. Now, let me give you a little visual. We'll be doing this in our lab next time, but a little visual of how it works on the next slide. Here's how the titration process works. First, you get a conical flask, and into that flask, you're going to pipette a very specific volume of one of the solutions. To that solution, you're going to add some indicator, and then you're going to take a burette that is filled with the second solution and measure its volume really carefully. You'll start dispensing that second solution into the flask until an indicator shows that the reaction is complete. And then you stop and you read the final volume on the burette. So what you end up having is two really precise volumes of the solution of each of the solutions used, and then you'll also know the concentration of one of those solutions, and that's enough information to find the concentration of the other solution. So let's look at an example where we do just that right now, where we do the calculations to find a concentration. So here's our example. In a titration experiment, 18.63 cubic centimeters of 0.150 molar NaOH is needed to neutralize 25 cubic centimeters of HCl. What's the concentration of the HCl? So there's our reaction. Acid plus base yields salt plus water. And our known information, we know both the volume and the concentration for the NaOH. For the HCl, we just know the volume, and so our goal is to find the concentration. Our calculations are going to have 3 steps. Step number 1, what we're going to do is we're going to take that NaOH solution, the solution that we know the concentration of, and figure out how many moles have reacted. And so we're just doing that using C equals N over V. And so that means if we're solving for N, the number of moles, N equals C times V. So our concentration is 0.150 moles per cubic decimeter. And our volume, this is cubic centimeters, we want cubic decimeters, so I'm going to divide by 1,000. I'm going to move my decimal 3 places to the left, and my volume is 0.01863 decimeters cubed. And multiplying that out, I get the number of moles of solution, which is 0.002795 moles. I'm going to keep a extra sig fig for right now until the very end. Okay, step 2 is to, now that I know moles of NaOH, I'm going to use my mole ratio to find moles of HCl. So this couldn't be more straightforward, right? We have 0.00279 moles of NaOH, and our mole ratio is 1 to 1. So 1 mole NaOH reacts with 1 mole of HCl, and so the number of moles of HCl that reacted was 0.002795 moles. All right, so now I have a number of moles of HCl and I have a volume of HCl. I have the information it takes to find the concentration of that HCl. So that's step 3. So step 3, again, use C equals N over V to find the concentration of the unknown concentration solution. It's a lot of concentrations in there, isn't it? So we do C equals N over V. Our moles of HCl we just calculated as 0.002795 moles. And then our volume, 25 cubic centimeters, is, move the decimal 3 places, 0.02500 decimeters cubed. And the concentration of the solution, then rounded to 3 sig figs, is 0.112 molar. Ta-da! We just did a titration calculation. Okay, let's do one more, just all the way through so you can see how it works. Okay, so this is another experiment. This time we have for H2SO4, 28.40 centimeters cubed, and the concentration is 0.137 molar. And for the KOH, we know we're using 20.00 centimeters cubed, and we are looking for the concentration of this. Okay, so same 3 steps, and we're always starting with the solution that we know both the volume and the concentration. So step 1, I'm going to use C equals N over V to solve for N. N equals C times V. So my C, 0.137 moles per cubic decimeter, and my V, 0.02840 decimeters cubed. That equals 0.003891 moles, and that's of H2SO4. Step 2, mole ratio. So I start with my 0.003891 moles of H2SO4. And this time my mole ratio is 2 moles of KOH for every 1 mole H2SO4. And so that is equal to 0.007782 moles of KOH. And my final step, step 3, is to use C equals N over V to find the concentration for that KOH. So it's 0.007782 moles over our volume is the 20 cubic centimeters, so that is 0.02000 decimeters cubed. And the concentration to 3 sig figs is 0.389 molar. All right, we did it. So when you break it down, it's pretty straightforward. And that is the end of our notes for today. All right, thanks. Have a great day.